Okay, we are going to start on our gases chapter. So gas laws, stoichiometry, kinetic molecular theory, all of it together. So we've actually been talking about gases a bit because we've been doing them in the lab. We're going to talk about them in greater detail now. So the first thing we're going to talk about is air pressure. So this is a barometer, what we're missing in our lab today, our lab this week. So when we measure air pressure, we use a barometer. And what it is it's a column of like an empty, like an evacuated glass tube. So all the air molecules have been removed from it. And this is like a bowl of mercury. And so remember, when we talk about pressure, we've talked about this a little bit. Pressure is just force over an area. So it's the air molecules colliding with each other and surfaces. And so the pressure or the air molecules are pushing down on our mercury here, which is forcing the mercury up the tube, while at the same time gravity is holding the tube down. And so this is where we get that unit, that 760 millimeters of mercury. That is where we get it. It is the force of the air on the surface of the mercury, and it counterbalances the force of gravity. And this distance is 760 millimeters of mercury. Okay, so let's look at this. What happens to the height of a column of mercury in a barometer as you climb to the top of the mountain? So remember, again, pressure is just molecules hitting each other or the container, right? So if we climb to a top of a mountain, right, there's less gravity. So the air molecules, so here's us. Here we are. We're at the top of the mountain. Yay. The air molecules here, I can draw a little bit better than that. Well, not much so, let's be honest. Now we're jumping off the top of the mountain here. The air molecules here at the bottom of the mountain are going to be much closer together than they are at the top of a mountain. This is why people need air when they climb to like Mount Everest, because the molecules themselves are further away from each other. They're not colliding as much. So the height of the column of mercury will actually decrease because there's less molecules hitting the mercury. So, right, the higher we up in the atmosphere, see, there's going to be less molecules forcing it up because the molecules themselves are further away from each other. Okay, so let's just do a quick example here. Just a quick unit conversion. I know that we're all really good at these. So a high performance bicycle tire has a pressure of 132 psi. What is the pressure in millimeters of mercury? So again, I would not have you memorize this. This would be something I will definitely give you. You're going to remember this one no matter what, just because you're going to be using it so much as we have in lab. So we just need to go from psi to millimeters of mercury using our unit conversion. So if we have 132 psi, again, the unit we want to get rid of goes on the bottom. 1 atmosphere on the top, units. 1 atmosphere is 760 millimeters of mercury. So just a little quick unit conversion here. And when we do this, we get 6.82 times 10 to the third millimeters of mercury. And again, all of our units cancel out. So this is kind of a cool little conversion you might want to remember here, or this kind of keep this like, hey, it's kind of all the conversions in one. So for Chem 101, you'll use these. For your lab, we've used some of these also. So kind of take a look at these conversions and kind of maybe keep these all together. You don't need to memorize them. I'll give them to you. But again, just make sure you remember these. Or use those, remember them when you're using your Chem 101. Okay, so if we want to convert from psi into kilopascals, we need to get those conversions, which here they are for you. Again, I would give you all these conversions. And then we just start with our 45.5. I think I just accidentally put this in here. So 45.5 psi, 14.7 psi goes on the bottom. atmosphere on the top. And we want to go to kPa. Again, this unit would be given to you, but for Chem 101, you need to make sure you have it close to you because it will not be given on Chem 101. It will on any quiz or exam. And then we just cross off our units, and we get 314 kPa. Now these unit conversions we've been doing so many of these. We should be pretty good with these unit conversions. All right, the next thing we're going to look at is a manometer. So a manometer is something we can measure pressure with. So it measures the pressure of a gas that is trapped. They're U-shaped tubes, and they're partially filled with a liquid connected to the gas sample on the other side and open air on the other. So there's this little competition going on, and it's between the pressure of the atmosphere and the pressure of the gas. So the difference in the liquid level is a measure of the difference in the pressure between the gas and the atmosphere. All right, so it's this competition between the atmosphere and the gas, the pressure of both of these. So here's a picture. So in this case, we have this looks like mercury to me in here, right? This silver looks like mercury. And so you can see atmospheric pressure, this is open, is pushing on this, but our gas is pushing this way. Right? So you can see our gas is pushing this way. And so in this case, this sample of the gas has a larger pressure than the atmosphere. How do I know that the gas's pressure is larger than the atmosphere? Because the gas is pushing further here. The atmosphere is only getting this distance. And so if I want to know what the pressure of this gas is, right, in all of this, it's whatever the pressure of the atmosphere is plus this height. So it's atmosphere plus the height that we have. And so that would be how we figure out the pressure of a gas in a manometer. And you're going to see a couple of these in your homework. Okay, now properties of gases. All right, so the properties of the gases. Number one, gases expand to completely fill their container. Right, and we already know this. Like if we have somebody in class, remember when we were in class, and they put on like this lotion, all of a sudden the entire classroom would fill with the smell of the lotion. Those are gases. They take the shape of their container. They have a very low density, because remember, density is mass over volume. So their density is very low because their mass is tiny and their volume is gigantic. They're also very compressible. So we could take all the pressure or all the gas molecules in the room that you're in, and we could fit them all in a coffee cup. That's how compressible gases are. And mixtures of gases are always homogeneous. It means they always mix completely and together. So this brings us to our kinetic molecular theory. So again, the kinetic molecular theory is just describing the behavior of gases. So gases are constantly moving, and the only time they slow down is when they hit the side of the container or each other. And technically, we say they never slow down. We say that they are perfectly elastic. And it also says that the attraction between particles are negligible. So that means if you have a gas that's positively charged, we're saying that it is not attracted to the negatively charged gas, and vice versa. And we're also saying a polar gas is not attracted to another polar gas, and vice versa with the nonpolar gases. It says that when the gas particles hit another particle or the container, they don't stick, but they bounce off and continue, like billiard balls, but more like, think of it when you were playing pool, if you played pool with bouncy balls. That's kind of how you can think of gases. They just keep going and they never slow down. Kinetic molecular theory also says there's a lot of empty space between the gas particles. And the average kinetic energy of the gas particles is directly proportional to the temperature. So if we raise the temperature of our gas, the molecules move faster. But they're not all moving at the same speed, right? They're not moving at the same speed. But if we increase the temperature, we do increase their speed. Okay. So let's look more about pressure. Again, the gas molecules are hitting themselves or the side of the container. And pressure, technical definition, is just force over an area. So technically here is our equation for our gases. The average kinetic energy depends on both the mass and the velocity, right? This is our mass. This is our velocity. And gases in the same container all have this, if gases in the same container, they all are in the same container, they have the same temperature, that means they have the same kinetic energy. But just because they have the same kinetic energy, that does not mean they are moving at the same speed. If they have different masses, the only way for them to have the same kinetic energy is for them to have different average velocities. So lighter particles will move faster than massive particles. Think of it like this. If you had, let's say you were exactly this, you had the exact same strength in both your left arm and your right arm. And in one arm, you had a ping pong ball. And in the other arm, you had a bowling ball, right? Greatly different masses. But if you throw both of them with the exact same force, because your arms are the exact same strength, they would have the same kinetic energy, but I guarantee you that ping pong ball will go a lot faster than that bowling ball. So they can have the same energy, but they do not move at the same speed because kinetic energy is proportional to mass and velocity. So really heavy things will move slower, but they will still have the same kinetic energy. So here is a little graph between molecular speed and molar mass. So to have the same kinetic energy, molecules that are heavier move slower, and this makes sense. Here's oxygen, right? Its molar mass is about 32 grams per mole. And here's hydrogen, right? It's about 2 grams per mole. Right, so hydrogen weighs a lot less than oxygen. Now, hydrogen has a much greater distribution because of its mass, but you can see in general, hydrogen molecules move much slower than oxygen. So right here, slow, fast. And it's just the relative number of them. So in general, hydrogen moves much faster than oxygen because its mass is much smaller. But again, they still have the same kinetic energy, but they are not moving at the same speed. Okay, so we can actually calculate the speed, and this is called the root mean square. And what we're going to do is this is the average velocity of our gas, right? And so we're going to look at these. And so this is our molar mass. This R is this is the 8.314 joules per mole Kr, and that's our temperature in Kelvin. Oh, here it is right here. Okay, and so this is going to be our molar mass. Now, this is super important. This must be in kilograms per mole, not grams. So I would say 95% of the mistake here, people leave their molar masses in grams. It must be in kilograms. And so we're trying to figure out is about what is the average velocity. So this is called a Boltzmann distribution. So like, this won't go back. Well, I guess I won't go back to that slide. So this is called a Boltzmann distribution, what we just saw with the gases. We're trying to figure out like what's the average velocity, like how fast does a gas move at a specific temperature. And that, what we just saw, that graph, that was a Boltzmann distribution. And this method is called the root mean square method, right? And so we're going to look at a couple of them. Oh, and here's another picture. So here's again slow, fast, and here's the fraction of molecules. So if we had to pick the average here, what speed would molecules travel? And we're going to actually use this Boltzmann distribution, this root mean square method, to find out what speed is this at a specific, so like at 300 Kelvin, what speed is oxygen traveling at? All right, so when we look at this, So remember, as the temperature increases, the velocity is going to increase. And as it increases, not all of the atoms are going to have the same amount of energy. That's going to be more distributed. And so if we look here, so this is all nitrogen. So nitrogen at 273 Kelvin, remember here, slow, fast. Nitrogen at 273 Kelvin is on average moving pretty slow. At 2000 Kelvin, it's moving much, much faster. Increased speed, increased temperature, increased speed. Okay, so let's use this example to calculate the root mean square velocity of methane at 25 degrees Celsius. So if this was methane and this was 25 degrees Celsius, let me just go back here, right? If this was 25 degrees Celsius, how fast would it be moving, right? So that's what we're going to try and do, and we're going to use the method, the root mean square method. Okay, so here is our formula. Remember, this needs to go in kilograms per mole, right? And this R is the 8.314 R, right? So we need to remember that. And our temperature is obviously going to have to go to Kelvin. So we just add 273. Not so bad. A quick way to go from grams to kilograms, by the way, what I do is I just multiply it times 10 to the negative 3. And now it's in kilograms per mole. So this is just a fast way to go to kilograms. Just multiply it by 10 to the negative 3. And remember, this R here is the 8.314 joules per mole Kr. So when we do this, I'm just going to make it really big. So we have 3 times 8.314 joules per mole K times our temperature, which is 298 K, divided by our molar mass in kilograms. Kilograms per mole. And we do this, we take the square root of the whole thing, and we end up with 681 meters per second. Now, you're going to notice these units don't quite exactly cancel out, and that's because this is a very physicsy thing. And so this joules per mole K, I'm going to rewrite it the physics way. You're gonna love it. This is joules, so remember it's joules per mole K, but I'm gonna write joules in the world of physics. Joules in physics is kilograms times meters squared over seconds squared. So that's our joules per mole K. This whole thing means joules. But if you look now, it works. K, moles, kilograms, and your meters and seconds, that's what we're left with. Squared. And we end up with our answer, which is 681 meters per second. And that's how fast we're moving. Okay. Okay, and so when we look at this, the mass of oxygen is 32, is twice the mass of methane at 16. And so that makes sense that the root mean square, the speed of methane is 681, right? Compared to oxygen's 42. So this would make sense that methane is indeed faster than oxygen. So you're going to be doing quite a few of these in your Chem 101. So the keys here, don't forget to turn this to kilograms. And this is the 8.314, not the 0.0826. Okay, next piece, diffusion and effusion. Okay, so diffusion, that's just things going from high concentration to low concentration. So like when we're in a classroom and somebody uses lotion and then the whole entire classroom smells like that lotion, that's diffusion. Effusion, see how I'm saying that so specifically different? Effusion is movement through a tiny hole. right? So the rates of diffusion and effusion of a gas are both related to the root mean square average velocity. So for gases at the same temperature, this means that the rate of a gas movement is inversely proportional to the square root of its molar mass. Basically, the bigger it is, the smaller, or not the smaller, the bigger it is, the slower it's going to move. The lighter it is, the faster it's going to move. So here's effusion. It's just movement through, a tiny hole, right? So effusion is literally through a tiny hole. Okay, so Graham's law of effusion is kind of a fun one. So here's the formula for Graham's law of effusion. And so what we can do is we can figure out the molar masses of our gas based on how fast or slow one molecule is to each other. Now, this equation can lead to like some interesting issues. And so I'm going to show you something when we do this that you're going to solve this using logic. Okay, so calculate the molar mass of a gas that effuses at a rate of 0.462 times nitrogen. So this is slower than nitrogen, right? If it said like 2 times nitrogen, it would be faster. Since it's slower, this molar mass is going to be larger than nitrogen, right? So a lot of times people have trouble figuring out, well, which one is A and which one is B? It doesn't really matter as long as you know where your answer is, because if you do it wrong, you just switch it and you do it correctly. So in this case, I'm just going to choose here. So here's my molar mass for nitrogen, right? And I'm going to solve for my nitrogen, or for my molar mass of my other gas here. So let's just set it up both ways so you can see what I mean. So the rate of gas A and the rate of gas B. So let's say it's 0.462. That's the difference. Equals the molar mass of, let's put B, molar mass of B here, and let's put nitrogen on the bottom. Now there is actually a theory to make this work every single time, but let's just try this and see what we get for this molar mass of this gas. All right, so we have to square this, so we have 0.462 squared equals molar mass over 28.02 multiplied by 28.02 multiplied by 28.02, and we get 5.98. Okay, now let's remember what we said. This gas is slower than nitrogen. If it's slower than nitrogen, this number should be bigger than nitrogen, right? So now, I should have made this smaller. Let's try it the other way. 0.462 equals our nitrogen, 28.02, over our molar mass, square root. Square both sides, 0.462 squared equals 28.02 over our molar mass. And we do this and we get, I'm just going to do this math real quick. So 0.462 squared times the molar mass equals 28.02 divided by 0.462, squared, divided by 0.462 squared, and we get 131. Okay, this one makes way more sense. So this is molar mass, grams per mole. So let's say you were unsure which one to do. It says here, this is 0.46 times. That means it's slower than nitrogen. If it's slower than nitrogen, the molar mass of this mystery gas must be bigger than nitrogen. This cannot be correct because that is smaller than nitrogen. This one must be the correct one because it is bigger than nitrogen. So if you're not sure, does it go on the top or does it go on the bottom? You can just use logic and decide and make sure, oh, I know my answer has to be bigger than 28.02, right? And indeed, it is. So if we go here and we look, indeed, our answer is bigger than nitrogen. Okay, so let's try another one. So calculate the ratio of a fusion for oxygen to hydrogen. Okay, so oxygen to hydrogen, right? So oxygen to hydrogen. So we want the rate of oxygen to hydrogen, O to 2. So when we write it like this, that's the same thing as writing it like this. Oxygen's molar mass, hydrogen's molar mass. Here again is what we're going to write. So we have a couple different ways to say if we want oxygen to hydrogen, remember, oxygen is heavier, right? Oxygen to hydrogen. Oxygen is heavier than hydrogen, right? And so therefore, oxygen should be slower than hydrogen, right? Oxygen should be slower than hydrogen. So it should be a smaller, oops, this one's wrong, here we are. It should be a smaller amount. So, okay, so let's say you calculated this the other way. So if you did this, you did rate of O2 to rate of hydrogen. Oxygen to hydrogen, so oxygen goes up here, that means the molar mass goes here because they crisscross. But let's say you did it wrong, and you did it like this. You know what you'd have gotten? You would have gotten 4. What does this mean? This means that oxygen is 4 times faster than hydrogen. And you have to think to yourself, what? That makes no sense. Because oxygen is so much smaller. I mean, so much heavier than hydrogen. So remember, when you're doing this, when you set this up, oops, let me just keep that cross out. The rate of A, the molar mass of A. So they crisscross each other like this. So if we have oxygen and hydrogen, it needs to be oxygen's heavier, so our answer should be smaller. So if we put oxygen here, the molar mass has to go here and vice versa. Okay, so on average, oxygen molecules are traveling at a quarter of the speed of hydrogen molecules. Okay, so now I want you to try this one. So try this one here, and then we're going to go over it together in just a minute. Even if, again, we're watching this recording, so you're watching this recording, make sure you pause it, try this problem, and then we're going to do this together, right? So if we go through here and you set this up, again, just make sure you crisscross those molar masses. And when we do this, right, this time we want hydrogen to oxygen. So we want H2 on the top, O2 on the bottom, equals the square root of the molar mass. Again, this is on the top here, so it's going to go on the bottom on the other side. Oxygen will go up here, and we solve this. So I'm just going to call this the rate, okay? Or the ratio, because I don't want to put them both up here. And when we solve this, we get 4. Yep, we get 4, which makes sense because hydrogen to oxygen, hydrogen is lighter, so it should move faster than oxygen, right? So this is the same exact question we just did, it's just backwards, right? So again, when you're doing these problems, keep in your brain, should the ratio be greater than 1 or less than 1, right? And then it'll help you figure out which one goes on the top and which one goes on the bottom. Okay, so now our next piece, we're going to talk about gas laws. So first, we're going to talk about Boyle's law. Boyle's law is an inverse gas law. So Boyle's law is pressure and volume. And as you can see here, as the pressure increases, the volume decreases. So when pressure increases, volume decreases. It's inversely proportional, meaning one goes up and the other one goes down. And again, when you see this on a graph, it always looks like this kind of curve. This means it's an inverse relationship, meaning one goes up and the other one goes down, right? And here is Boyle's law. P1 V1 equals P2 V2. And again, you definitely should have seen this before because you saw this in either intro chem or your high school chemistry class if you took high school chem. So we look at this on a molecular view. So pressure, again, is the molecule sitting the side of the container. So when we decrease the volume, what we're doing is the molecules are now hitting the container more often, right? So here's our first volume, here's our second volume, P1, P2. We've decreased our pressure, and so now the molecules are hitting the sides of the container more often. If they hit the sides of the container more often, it increases our pressure. So if we decrease that volume, we increase that pressure. They are inversely related. This brings us to Boyle's law in diving, right? So if anybody's gone diving, which I never have, but for each 10 meters you go, the pressure increases by 1 atmosphere. So when you go 20 meters down, that's like 3 times the atmospheric pressure that it is right now where we are at sea level. So if your tank contained air pressure at 1 atmosphere, you wouldn't be able to inhale it into your lungs, right? And so the only force we can overcome is about like 1.06 atmospheres, which is pretty much nothing. And so that's why people have to have pressurized tanks when they scuba dive, because as we pressurize to the level that they're at. And so that's why they have a regulator. So it regulates the pressure, and it makes the pressure around you the same as in the tank that you're breathing. So you're taking the air pressure is even that you're taking into your lungs. And that's why they have that regulator on them, which you scuba divers probably know exactly what I'm talking about. Okay, so let's look at this problem. And so with these problems, it's really helpful. You have to identify your variables. And so this is a cylinder with a movable piston, has a volume. So here's our, here's our volume. This is our V1. Here's our P1, and here's our V2. And again, you've probably done a lot of these. Identify your variables, write your equation, and then solve. And then we just plug them in. Make sure all those units cancel, and indeed, this one makes sense. It makes sense, again, if we look at this. Here's our second pressure, here's our first pressure. So our pressure went from 5 to 1, so our pressure decreased. So our volume should increase because they are inversely proportional, and indeed it did. Look, our volume was 7, now it's 21. Our volume did increase, and they increase by the same factor, or one increases, the other one decreases by the same factor. All right, let's look at Charles' law. So Charles' law is looking at volume and temperature. And by the way, how we remember these, now it sounds kind of silly, but we always say Boyle. Boyle is the VP, he's like the vice president. And we say that Charles, he likes to watch TV. Kind of helps a little remembering of this. And so volume is directly proportional. Directly proportional means if one goes up, the other one goes up. If one goes down, the other one goes down. That's directly proportional. You can also say the difference between direct and indirect like this. If they're on top of each other, they are direct. If they are next to each other, they are inverse, right? This is what an inverse equation would look like. This is a direct equation. Also, remember, everything is in Kelvin. This whole entire chapter, Kelvin, 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 Kelvin. So here's a picture of Charles' law, and you can see, you can always look at it, you can always see a direct graph. It's always a straight line up. It is direct. If we increase our volume, we increase our temperature. One goes up, the other one goes up. And technically, if we could extrapolate all these, it should go to about negative 273, which is what we call absolute zero. Never quite happens, but it gets close. Charles' law, again, if we look at a molecular view, so again, the pressure of the gas inside and out at atmospheric temperature, same temperature is the same. If we decrease the temperature, that means that the molecules inside, they're now moving slower. So they're hitting the sides of the container, which is the balloon, less frequently. If they're hitting the sides of the container less frequently, the balloon is going to start contracting because they don't hit it as hard, the balloon will actually contract. Now, if we increase the temperature, boiling water, now these molecules are going bonkers in here. And they're hitting the sides of the containers like crazy now, right? Which expands the balloon. Increase temperature, increase volume, right? Okay, so let's try this one. Do you see these Celsiuses? We can't have these. Every time you see Celsius, convert it to Kelvin. Like, it just needs to be like second nature. These all just have to go straight to Kelvin. So when we do this, we have T1, T2, V1. What is V2? Right, we assign our variables, figure out our equation, always convert to Kelvin. Now, a lot of times we'll use 273.15 Kelvin. That's completely fine. Sometimes we leave off this 1.5. I'm kind of impartial to which one that you do. And then we just solve for this, assign all of our variables, convert to Kelvin, right? So here's the temperatures we're going to be using, and solve, and we get 17.5 liters. And now let's look at the logic of it. So if we look at our two temperatures, our temperature was low and it got high. So we increased our temperature. So therefore we should increase our volume. We started at 10, we ended at 17.5. Yes, that sounds correct because it's a direct relationship. One goes up, the other one goes up. Okay, our next one, Avogadro's law. Some people like to call it Avogadro's law. Amadeo Avogadro, coolest name ever. He figured out the relationship between volume and the number of moles. More gas molecules, larger volume. Increase the moles, increase the volume. You can see direct relationship. One increases, let's increase our moles. Our volume also increases. Right? Double one, double the other. And this doesn't really matter the volume of the gas or the identity of the gas, and we're going to talk a bunch more about that one. But this is a direct relationship. So again, here is our relationship for Avogadro's law right here. And so same as the other gas laws for these, you first assign your variables, solve your problem, and there you go. Okay, so now I'm going to pause this, and I know you're watching this as a recording, but I want you to try this problem and then do your answer and then unpause. So make sure you pause it right now, try it, and then I'll go over it in just a minute. All right, so when we try this one, assign our values. Okay, this one was a little bit tricky because it says how many moles must be added to give 6.48. Right, so we're asking how many were added. So we need to figure out, this one's a little bit trickier than normal. So we solve for our moles, right? So we have, here's our N1, there's our V1 and our V2. So we're gonna solve for V or N2, and we get 3.41 moles at the end, but specifically it asks for how much was gonna be added. So we started with 2.25, we ended with 3.14. All we need to do is subtract those two to get the number of moles we actually added. Okay, okay, and so this is Avogadro's law. So we've done Charles, Boyle, so we'll do Dalton soon, and then we'll do Avogadro's law. This brings us to the ideal gas law. So hopefully so far all of this is review. So I'm going through it quite quick because we've done this before. So the ideal gas law is the combination of all of our gas laws. And so I always tell people you don't need to memorize the individual gas laws because everything is in the ideal gas law. So remember, we're going to use this R, right? And when we use the ideal gas law, our units must be in atmospheres, they must be in liters, they must be in moles, and they must be in K, right? There's no ifs, ands, or about when we use the entire ideal gas law. When we're using the individual gas laws, it's fine. But when we use the ideal gas law, it has to be in those units. Okay, so here is our ideal gas law, right? And we've already been working with this in lab, so it's not too unfamiliar. Okay, so let's look at this problem here. How many moles of a gas are in a basketball with a total pressure of 24.3 psi, the volume is 3.24 liters, and the temperature is 25 Celsius. Well, first of all, that has to go to Kelvin, and that has to go to atmospheres, right? Those things have to happen no matter what. Because whenever we use PV equals nRT, we have to make sure our units are in atmospheres, liters, moles, and Ks. So whenever we use all of these, and how do we know we're going to use all of these? We look at how many moles in a Pascal, pressure, check, volume, check, temperature, check, and we always have R. So we're going to use all of PV equals nRT, so we need to make sure we convert everything into the units that R is. So we need to make sure we convert everything into these units. So our pressure, again, this is a conversion. If you had this on a quiz or exam, I would give this one to you. So we convert that to atmospheres. Temperature, we just add 273, rearrange, plug in our variables, and we get 0.219 moles. And let's not forget our sig figs, right? 3 sig figs, 3 sig figs. We tend to forget those sometimes. And if you look, indeed, all of our units do cancel out. So that's the ideal gas law. We've really done this a few times now. And so we're going to talk more about this. We're actually going to talk a lot about this little fun thing here in just a minute. 1 mole at STP occupies 22.4 liters. We're actually going to talk about that in a bit also. Okay, standard conditions. This is a very important thing when we're talking with gas laws. So we see this as standard temperature and pressure. So standard temperature and pressure is 1 atmosphere and 0 Celsius, or 273 Kelvin. Whenever you see STP, it is shortcut for these two numbers, right? It's just a shortcut. So instead of writing these numbers here, we just get STP. I get the question all the time. They're like, they're not giving me temperatures and pressure. I'm like, it says STP. They are giving you pressure. They are giving you temperature. So remember, that's what STP means. Okay, let's try another quick question. This is not at STP. So we can see here's a volume, a pressure, and a temperature. And we want to know what volume it will occupy at, oh, there, I guess it is, standard conditions, right? So when we look at this, standard conditions, 1 atmosphere and 273 Kelvin. So let's look at what we've got here. PV equals nRT is kind of like your go-to for all things gases. So we've got a volume, we've got a pressure, and we have a temperature. Oh, look at this. We have volume, temperature, and pressure, and now it wants to know another volume. So this must be a P1V1 question. Okay, so you don't have to memorize what it is. You just need to remember this. Since this is PV equals nRT, we're only using PV equals PV and T. So cross everything else out, put everything on the left, and here is our new equation. P2 V2 over T2. Again, this works with every single ideal gas law or non-ideal gas law problem. Let's just say, let's pretend it only had, I don't know, let's say it was just P's and V's. You cross this out, and then you mirror it to the other side. P1 V1 equals P2 V2. Or let's say it was only P's and T's. Cross everything out, put everything on the left side, and then mirror it to the other side. See, you don't need to memorize any of those equations. All you need to know is PV equals nRT. Okay, so let's look at this problem. So we've got V1, P1, T1, and it wants standard conditions. So that's going to be P2 and T2, and we want V2. Right, so here's our V1, our P1, and our T1. Here's our P2 and our T2, and we're looking for our V2. And again, we can just rearrange PV equals nRT to solve our problem. Okay, so if we have, again, P1, well, let me just do that again. So if we have PV equals nRT, we've got P's, V's, and T's here, right? So we've got 2 V's, 2 P's, 2 T's. So, oops, let me write this here. P's, V's, T's, cross off R, put everything on the left. P1, V1 over T1 equals P2, V2 over T2. And we're solving for V2. So when you solve for this, I think it's easier to do it like this with the crisscrosses. So it ends up being P1, V1, T2 equals, crisscross it this way, P2, V2, T1. We're solving for V2. So we divide by P2, T1. So P2, I'm going to do this a little bit over here. P2 equals, not P2, sorry. V2 equals P2, V2, T1 over, yeah. I just multiplied that wrong. Let's write it down the right way instead of the wrong way, sorry. P1, V1, T2 over P2, T1. There, that looks a little bit better. But we have to make sure we convert everything. Actually, they just need to be the same. They don't necessarily have to be in liter, atmospheres, moles, and K because we're not using R, but they do need to be the same. What does that mean? Okay, so see how this is in PSI and this is an atmosphere? They have to be in the same because we need to cross them off. These both definitely need to be in Kelvin. Convert this one, 44.1 PSI. And there's 14.7 PSI in 1 atmosphere, which gives us 3.00 atmospheres. So we definitely need that. So when we plug this in, our P1 is 3 atmospheres. Our V1 is 10 liters. I'll worry about my sig figs later, okay? T2, 273 Kelvin, has to be in Kelvin. Not an option, has to be in Kelvin. P2, 1 atmosphere. Right, I'm just reading these up here. T1, 300 Kelvin. You really got to keep these 1s and 2s straight. Really got to keep them straight. So we put that in our calculator. And we get, so 3 times 10 times 273, what's this, divided by 300. We get 27.3 liters. So solve this using PV equals nRT. Just this way just looked a little easier to me. Sometimes there's a lot of different ways you can actually solve these problems. Another one, calculate the volume occupied by 637 grams of SO2, gave you the molar mass, at that pressure and that temperature. All right, so again, PV equals nRT. That's our go-to for everything. PV equals nRT, PV equals nRT. So we've got a pressure. Whoa, we've got a pressure. We'll look at the molar mass in a minute. We've got a temperature. We want volume, and we have 637 grams. Oh, well, we can just go from grams to moles, right? That's easy peasy. We always have R. Okay, this is just V equals nRT over P. We just have to convert this grams to moles. This has to go to atmospheres. And that has to go to Kelvin, right? Because remember, R is 0.08206 liter atmospheres per mole K. So if you use R, you have to use these units. You must use those units. Okay, so again, we're going to need to get rid of those grams. We got to get those to moles. So we just use our molar mass, easy peasy, convert it to moles. Got to have our pressure has to be in atmospheres. Our temperature has to be in Kelvin, and then we just plug it in, and we get 2.55 liters. And we check our units, and they do all indeed match. So again, the key is, and do you see here how I use 0.0821? That's fine. Like sometimes, and you've seen this in lab, you can use either number. This one's just the rounded one, right? We just rounded this to a 1. I don't care which one you use. Your answer is going to be close enough. So it's okay if you use 0.0821 versus 0.08206. Either of those is going to be fine. We're going to stop there. So what you should know by now is you should be very clear on kinetic molecular theory. Make sure you read that in your book. You should be good with the individual gas laws. Again, read those in your book. And the ideal gas law. Right, so those are the 3 things we've kind of done. This should be all of your your prior Chem 209 or intro chem knowledge. We kind of wrapped it all up here. So we're going to start with a bit of new stuff on our next lecture. So make sure you are prepared with your new lecture. You're good with all the gas laws, ideal gas law, and kinetic molecular theory.